Okay, I'm going to get started. So today is our second of two lectures on segmentation. And if you recall from last time, the way I like to break up the world of segmentation, there are two general approaches. One of them is called bottom-up, and what you try to do is basically describe similarities between pairs of pixels and see how that percolates up into sets of categories. And in the other one, it's called top-down, in which you impose at least somewhat of a preconceived notion of both how many different categories of pixels there are in the image and other properties of them, what their general shape is, where they might be located, and so on. And again, just to really review, the problem of image segmentation is to assign each pixel in your image to one of a small number of categories, where each category corresponds to pixels that belong together in some sense that is up to you, the engineer, to define. So, by the way, the U book, Chapter 9, is actually a pretty good read when it comes to top-down image segmentation, turns out. And obviously, the U book is supposed to be the theory behind what is implemented in ITK. So there is a pretty good correspondence between what you read about in U and what exists in the Insight Toolkit. Now, top-down segmentation, the way I'm going to present it to you, it makes use of a technique called deformable contours. Yeah, it sure doesn't. Does it show up at all? See these little red dots, hopefully? I think the people who are learning from a distance are totally out of luck. But I'll explain this figure when I'm done with this slide. So basically, deformable contours, like I said, basically in top-down segmentation, you start with some preconceived notion about how your categories of pixels are situated in the image. And in particular, if you already know how many categories of pixels there are in the image, and you start off with a somewhat of a notion of where the boundaries between these categories of pixels are, and if you assume that each of the groups of pixels have a somewhat simple shape, in other words, it doesn't look like popcorn, or what do you call that, like a television static pattern where you have category 1, category 2, category 1, category 2, and a kind of a somewhat random or checkerboard pattern. If they have a simple shape, they're kind of blob-like. Or if you want to segment the image interactively, you can use this technique called deformable contours. Now, what the red dots are supposed to be showing you is 4 screenshots of interactive segmentation, where here, simply put, we have two categories of pixels, the white ones and the black ones. And what a user wants to do is not leave it up to chance that an automated algorithm is going to correctly identify which ones are the white ones and which ones are the black ones. Obviously, this is a toy example. You can simply segment the image based on a threshold that goes somewhere between white and black, but just for the sake of argument. Imagine that the user is able to click points in the image. That's what's supposed to be in red here, where they've clicked a couple of points here, and what they're doing is basically clicking points that go all the way around this object of interest to give a rough indication that the stuff inside that loop of red dots is one category, and roughly stated, the stuff that's outside of it is in a different category. Then you can use what's called deformable contours to isolate one category from the other. So, in order to use this technique, you will need to settle 3 different design choices following my usual approach of telling you, the computer scientist, what your recipe is for applying this technique in practice. The first thing you need to do is define a parameterization. And so the notion here is that whether you click it manually on the image yourself as a human being, or if perhaps you have an automated process that comes up with an initial set of points that represent the boundary between one category and the other, you're still going to have a starting point, which is that you have a set of points in the image that form a closed boundary which is going to be basically your closed contour around around one of the categories of interest. So if you do that, then the first thing you need is a parameterization of the entire boundary that is represented by those points. So the idea is that you have a set of points that are shown in blue, and you might have these spaced in some spacing around the entire boundary. So what you need to do is basically fill in the rest of the boundary in between. And the way to do that is to do what's called parameterization, and that's your description of what the contour is mathematically. And you have to decide what the functional form of that boundary is going to be based on those points, and how many parameters it's going to have, how exactly you're going to parameterize it, and that kind of thing. And so, for example, imagine that you have a functional form for your boundary that just takes one variable called s. Then you can imagine having two functions, x of s and y of s, that for every s, say between 0 and 1, give you an x comma y that corresponds to one of your points on the contour. So maybe s equals 0 corresponds to this point of the contour, and then you have s equals 0.1, 0.2, 0.3, 0.4, 0.5, and then all the way back to, okay, maybe s of 1 corresponds to your starting point again. So it's describing the contour in a mathematical form. The second thing you need, and by the way, we will now, once I give you the recipe for the three things that you need to solve in terms of design choices, we'll go through various, choices, your various options for how you can decide those design choices. The second thing you need is to define what's called a contour energy. So this energy term, or when I call something an energy, it's because, again, we have hijacked a bunch of material from another scientific discipline, in this case physics. So the idea here is that the contours that describe the boundary between your two categories of pixels are not real in any physical sense, right? They don't represent an object in the real world, but you are going to ascribe to it properties that are typical of objects in the real world. And in particular, you're going to ascribe each possible boundary in the image an energy. So one simple way to think about this is that a rubber band is a boundary in some sense. And if you stretch the rubber band, it has more potential energy in it, right? Because you have converted the kinetic energy of you pulling into the potential energy that's stored in the elasticity of the rubber band, right? So a stretched out rubber band has higher energy, and a not stretched out rubber band has lower energy. So you can think about that maybe as your analogy for what I mean by an energy associated with a contour. So, however, while we think about contours as having energies in that sense, how we define the energy for any given contour is completely defined by us. So it's not simply defined by Newton's laws or by Maxwell's equations, but it's defined by you, the engineer, to encode what you want these contours to do. In other words, they encode your notion of how well the contour is fitting around one category of pixels as separated from the other category of pixels. And by the way, I usually talk about top-down segmentation in terms of cases where you only have two categories of pixels, but it's not hard to extend this to cases where you have 3, 4, 5, 6. So it quantifies what you want the contour to do. And let's say that you have that previous example of the kind of chess piece shaped image, and your initial contour, either automated or manually described, is this one. Well, then you can just decide, because you are the engineer, the computer scientist, that this corresponds to a relatively high energy contour, and this corresponds to a relatively low energy contour, because it's doing what you want it to do. So this is the part where we, the image processor, starts with a semantic notion in some way of what the boundary between the two categories is, and here is where we are stuffing that thing into mathematics. So one notion could be that you have a low energy contour if it is hugging the boundary between a bright region and a dark region. That's just one possibility. Another component of this energy could try to encourage simple shapes, like this one, and discourage complicated shapes. So this is kind of more along the lines of the rubber band example, where if you imagine that you have many fingers, 15, 20 different fingers, and they're all pulling and or pushing the rubber band in different ways, well, all of that stretching and tugging is going to really increase the potential energy of the rubber band. And in your image, you might know a priori, beforehand, that your category of pixels always correspond to relatively round blobs. And so you want to disallow very complicated contours because they just don't occur in the types of images that you are processing. And so you can then, by decree, decide that a contour energy is going to be high if it's relatively complicated and lower if it's relatively more blobby. And you can compose these things together. So you can imagine that you might want both. If you know that you have bright blobs on a dark background, then you can decide to add two kind of components to your energy function that say that, well, the energy is relatively low if the contour hugs a light to dark boundary and it's relatively round and blobby. Does this notion of an energy make sense? Okay, good. Now the third thing you need to do, yeah?
Sorry, does the contour have to be a closed loop?
Not necessarily. I think all of the slides in this presentation correspond to closed contours. And that's because in some cases that makes things a lot easier for you. And I'll just give you one example. I think it's actually in the slides later on. But one concrete example is that it's pretty common to want to start with an initial contour. Actually, well, this is a good example. So it's fairly common to start with an initial contour that's too big and want it to shrink wrap in the saran wrap sense around the object of interest. And so closed contours are nice because you can always define an inward direction. So in fact, you can decide that you want to add another energy term to this that says smaller contours have lower energy. So they're always trying to get littler and littler. And that's hard to define for a not closed contour because there isn't an inside and an outside. So that's why closed contours tend to be sort of relatively more predominant, but outside of that particular case, they're not forbidden by any sense. Any other questions? Okay, so the third thing you need to do is just a numerical mechanism for turning the crank, which is to say, find contour parameters that minimize the energy. So this is optimization. It's some people would refer to it as a black art or sort of a dark side of the force type of thing because a lot of times they're just black boxes. So we will typically write the code that encodes our notion of energy and our notion of parameterization. We oftentimes do not write our own code to do optimization. In fact, we often feed them to one or another different optimizer that is sitting there on disk somewhere. So, however, just take it for granted that there are optimizers out there that can sort of turn the crank, start with an initial set of contour parameters, such as is suggested here, and get you new contour parameters that minimize the energy. For example, if you have that kind of light to dark boundary energy. So, parameterization, energy, and optimizers. Here are the kind of results that you can get. Deformable contours really kind of blossomed in the early 80s. And because they are useful for a variety of different applications, it's fairly common to, for example, in abdominal CT scans, I think these are both kidneys, and this is someone's abdomen as they are laying down on the table. It's fairly common to want to isolate just an organ of interest, such as the kidneys. And what is fairly common nowadays, and in fact the software comes with your $2 million CT scanner as after you write your check for it, to simply plop down something like a sphere, an initial contour that's round, and it has the opposite of the shrink wrap thing, where it's called a balloon, where one of its energy terms simply tries to make it get bigger and bigger and bigger and bigger. And if you do that, it takes almost no time at all for some technician to sit there and go boop, and then have the contour expand until it finds a dark to light boundary, thus isolating the organ of interest from the abdominal fat and other soft tissues. On the right, you see the kind of more computer graphic-y, artsy applications of deformable contours, where you have a painting that has been scanned in by somebody, and they want to manipulate it in some way. And so, in fact, a quick and easy way to say this is that Magic Lasso in Photoshop does exactly this. You kind of wave the cursor and click it in the general vicinity of your boundary, and it sucks onto it. That's exactly what a deformable contour is, and it does a lot in terms of being able to allow you to blue screen out the background from the rest of a photograph. Yeah?
Is this what are also called snakes?
Yes. If you want to go back into the literature and look at the historical papers on this topic, especially the not closed contours are called snakes, because when you see them over the course of optimization and they move from one position to another, they really do wiggle, and they move around like snakes do. And in fact, I think the seminal paper on this topic may have just been called Snakes for Deformable Contours or something like that. Okay, so if that sounds all right to you all, then I will go on to talk about different ways of doing the parameterization and different ways of doing the energy function and different ways of optimizing. I'm not going to spend a whole lot of time on optimizing because, again, it's assumed to be kind of a black box. Before I do that, I don't really have any announcements about administrative things. Does anyone have any administrative things related questions? Okay, so, and by the way, let's see, Jing's office hours are after this, so you can ask her about homework 1 at that time. All right, so parameterizations. I will talk about 3 different ones. The simplest one is called a piecewise linear parameterization, where here you have a set of points that you have identified, or that are initial starting points for your deformable contour. I call those capital C, so C1, C2, C3, C4, and so on. And what you want to do is very simply define the boundary in between C1 and C2. So the most simple way to do this is to just connect C1 and C2 with a straight line. And then you would have a parameter S. And really, this should be something like S12 that varies between 0 and 1. And for S equals 0, you are at C1. And for S equals 1, you're at C2. And what you should be able to do is look at these two equations and determine that when S equals 0, the C1 drops out. Let's flip what I just said. So if S is 0, the C1 goes to 0, and you're at C2. And if S is 1, then this part goes to 0, and you're at C1. So if, like I said, so if S, think the opposite of what I said previously. So if S is 0, you're at C2. And if S is 1, you're at C1. And it shouldn't be hard to see that if S equals 0.5, you're halfway in between them. So the idea here is that for every pair of these points, and by the way, these are usually referred to as control points, because the points control where the contour is. For every pair of control points, you are going to have an equation like this. So in order to define the entire contour, you're going to have, I guess if there are n control points, you're going to have n minus 1 of these S parameters for every gap in between every pair of adjacent control points. And that will fully define, those parameters will fully define the entire contour. So it's very, very simple. It makes really very few assumptions about what legal contours are, because it's simply drawing a straight line in between them. If you think about it, the contour in between the control points is not really defined a priori. You're defining what it is, and so it could do a lot of different things in between here. But you're making things very simple by just connecting the adjacent control points with a straight line. The math becomes very, very simple. Now, one potential problem here is that if let's say that you want to have a nice, smooth, relatively round, circular sort of contour. And you have a lot of points, you have a large number of these control points that are densely packed together. Then if you have enough control points and you start with, for example, something that's circular, then it'll look circular. Because if the density of points is high enough, then the fact that there is a straight line between them won't make it look like a polygon. From a distance, it'll look like a sphere. However, imagine a case like I just talked to you about, where you start out with an initial little sphere, and you expand it and expand it and expand it. Then what's going to happen is that the spaces between adjacent pairs of control points is going to get bigger and bigger and bigger. The density of control points is going to get lower and lower and lower. And so as the sphere gets bigger and bigger, you're going to end up with something that looks more like a polygon with sharp edges, as opposed to this round, blobby-shaped thing that you wanted. So that is one potential limitation of using what's called a piecewise linear parameterization. It should be obvious why it's called piecewise linear, because you're breaking the entire boundary up into pieces, each one of which is determined by, or which is described by a linear function. So there's a lot of parameters, by the way. There are basically 2 per point in 2D for each x and y position of the points. And figuring out one particular spot, if you wanted to iterate through the entire contour, then you have to think about these S parameters for each possible pairing of adjacent control points. The next most complicated thing is to use what's called splines, where instead of simply connecting the adjacent control points together with a straight line, you can think of the obvious generalization of connecting them together with a not straight line. So again, the contour parameters are these point positions, C1, C2, C3, C4, and so on. But the way you determine what the position of the boundary is in some place that's in between the control points is to use a more complicated function than simply connecting them with a straight line. And in particular, you use a thing called a blending function. So a blending function can be thought of as a kind of a weighting function for each one of the control points. So specifically, imagine that you define your entire contour as being parameterized by one single parameter S that lies between 0 over here and 1 all the way on the other end. And for any given S between 0 and 1, you're going to want to determine where exactly the boundary is for that value of S. So for an S value of 0.5, you want to find the location that's halfway along the contour, for example. Then what you would do is use this blending function that gives a relatively high weight to control points that are close to that middle of the contour, and a relatively low weight to control points that are far away. So if you asked for the position of the boundary for S equals 1, you can imagine that, and if that corresponds to the end over here, then you can imagine that what it's going to do is weight C1 and C2 relatively low, and rate C3 and C4 relatively high. And what you're going to do is basically take a weighted average of those point positions to get that point position that you have at the end there. And so really, in terms of defining how wiggly your contour can get, it all comes down to selecting this weighting function. And I don't have it on this slide, and I keep forgetting to add it to it, but there are basically 2 types of spline parameterizations. One is called an interpolating spline, which is to say that the blending functions are defined such that the curve always goes through C1, C2, C3, and C4, and so on. And the other one's called an approximating spline, where you define where these control points are, and the spline does the best job that it can to get as close as possible to going through C1, C2, C3, C4, and so on, but it's not guaranteed to. And in particular, what you can do is force the spline function to be very, very, very smooth. And if you do that for an approximating spline, you'll get something that goes more like this, and really fails to dip down and get as curvy as this one. And that'll happen if you use an approximating spline that is very, very strict about the curvature of the thing. And I would add that from the computer graphics world, from the 80s and 90s, there's a whole literature on different types of splines, and they all have their own fancy little names, and they all have different properties. But this is the basic idea, that you're going to interpolate in between your control points with some function that is not necessarily linear. Okay, now this is usually the one where I lose people. It's the third possibility in this presentation for how to parameterize your closed contour, and it's based on that thing we talked about in the very first lecture, which is the Fourier Domain. So, in order to construct this particular parameterization, what you do is you can imagine yourself walking along the contour, starting at, say, 3 o'clock over here, and walking along the contour, and for every step you take, you make a note of the x-coordinate where you are and the y-coordinate of where you are as a function of how far you have walked. So at the very beginning, your x-coordinate is some medium-high value, and the y-coordinate is 0. So I kind of did that sideways, but what you can do is plot your x-coordinate as you're walking along in one plot, and your y-coordinate as you're walking along in another plot. So let's see, I guess this point would correspond to here. And as you go away from that, your y-coordinate keeps going down, 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 down. And this point here would correspond to over here, and then you would keep coming down like this over here. So what you can do is then look at these functions, x of t and y of t, where t is your measure of how far you have walked, and think of them as simple one-dimensional functions, just like those one-dimensional slices of images that I showed you earlier in the quarter, for which you might consider doing a Fourier transform of those one-dimensional functions in order to tell the story of that function in terms of its frequency components. So then, like as we talked about earlier, surely you remember this, you can convert any function in this particular spatial domain into components that are in the Fourier domain. And remember that we can flip back and forth between this spatial description of the contour and this frequency description of the contour. So you might be asking yourselves, why on earth would I bother taking my two-dimensional contour and converting it into two one-dimensional functions, which I then take the Fourier transform of? Well, the reason why is that, just like with image smoothing, you can reduce high-frequency components of the Fourier transform, go back into the spatial domain, and you end up with a low spatial frequency thing. So simply put, what you do is you take your initial contour, which is wiggly as can be, you convert it to the Fourier domain, shut off the high frequencies, and go back, and you'll end up with a simpler shaped contour, because you have removed the high frequency fluctuations in the x-coordinate and the y-coordinate. And furthermore, one of the nice things is that if you have a contour that has 50 control points in it, and it's shaped like a sphere, you still have 50 times 2 parameters, even though it's a sphere. If you take that same contour and add a lot of fluctuations to it, you still have 50 times 2 parameters in it. Anything in between, everything that's partially blobby, still has 50 times 2 parameters in it. Well, what this does is it allows you to reduce the number of parameters that you need to describe the contour based on how high frequency it is. So if it has a very small, if you really don't want a lot of fluctuations in your boundary, you can simply restrict the boundary to only having very low frequency components. So in other words, you only have to keep track of the low frequency Fourier coefficients. And this is useful, for example, if you care about how concise your description of the contour is, for example, for transmitting it across a communication line. So then the kind of loaded question is, how high frequency should you allow your contour to be? And this is one of those magic design decisions that there's no good theoretical answer to. It depends on what your data looks like, and it depends on what kind of contours you expect to see in your image of interest. Does this make sense? Okay, great. Okay, we have talked about 3 different ways of parameterizing these contours. Now let's talk about this energy function, where what you are trying to do, again, is impose your own law of physics, if you will, onto your contours to encourage certain types of behavior and discourage others. The kind of behavior that you are discouraging gets assigned high energy, and the kind of behavior that you are encouraging gets assigned low energy. And then what the optimizer is going to try to do is try to find parameter settings that minimize that energy. Now, one very common approach is to use this formulation that is up at the top, where basically for every position in your contour, let's say that you have one parameter for your parameterization of the contour, and that's S, then each S corresponds to one position on your contour. Okay? So then what you can do is then integrate some energy function over the entirety of the contour. So if you just look at the fact that there's an integral and a bunch of stuff that depends on S, and you're integrating over ds, then you're integrating for every position on the contour, you get a sense of the energy, and you're integrating that thing over the entire contour. So you're kind of summing up all the contributions of all the points on the contour, and the thing that you're summing up has this 3 terms in it. E internal, E image, and E user. So alpha, beta, and gamma are ways of upweighting or downweighting the contribution of any of these terms, which I will describe, for any point on the contour. So it could be that depending on your application, you might have certain points on the contour that you are absolutely that it's just absolutely so important for that thing to fit properly and to have the right characteristics, and other parts of the contour are not so important. So for the points on the contour that are not so important, you can then put this alpha to be a low weighting factor, and for the points that are important, you make it a high weight. So then what you're doing is adding up 3 terms, internal, image, and user, in terms of what the energy of any particular single point on the boundary is. And then what we're going to try to do at optimization time is minimize this integral by finding different parameter settings. So let's go through these 3 energy terms independently. And by the way, the thing that's nice about this energy formulation is that you can just tack on more and more terms. If there's 3 different things that you want your contour to do, you can have 3 energy terms. If there's a 4th thing that you now want it to do, then you add a 4th term. So what I'm telling you is that there are 3 different characteristics that I want my contour to have. I'm going to talk about each one of them. So E internal, that's what's called the internal energy. So this says, regardless of what the image looks like, there are general shape properties that I think are favorable that I want my contour to have, regardless of how the imaging data looks like. The image could look like anything. And for example, what you can do is say, I want the boundary to have continuity. I don't want corners, and I don't want cusps. So remember from calculus that at a corner or a cusp or at a step discontinuity, what happens to the first derivative of a function? Goes to infinity. And if you have the contour that minimizes the first derivative is basically as flat line as possible. So it's continuity, which is basically saying we minimize the first derivative of the contour with respect to S. So as you're moving along, it doesn't change very much. Smoothness is only very slightly different in that you're trying to minimize the magnitude of the second derivative. And what this is doing is trying to minimize the curvature, which is to say it's trying to minimize the degree to which the contour is wiggling in a high frequency way. And usually what you can do is approximate this second derivative by taking the point position for one contour point, if they're closely packed together, and taking this linear combination of -2 times my point that I'm at, plus the points that are on either side, which, if you plot that out, looks like a kind of a Mexican hat operator. Again, it looks like a Laplacian of Gaussian. So you're really taking the second derivative of the contour, at least a discrete approximation of it. So this should be kind of generic. It's just saying that I want well-defined curves that do not fluctuate too quickly. The image energy now adds in how you want the contour to relate to the imaging data. So this is how you can mathematically define the fact that you want the boundary to be the boundary between a light region and a dark region, or between a red region and a blue region, or between a plaid region and a polka dot region, for example. And if you if the thing that you want is to have the boundary lie between one flatly shaded region and another flatly shaded region, what you can do is say that the contour has low energy if the gradient of the image is very high. So remember, if the gradient is very, very high, that means that you're at a boundary between either between dark and light or between light and dark. So that's what this will do. This upside down triangle operator is the gradient. So it's basically the first derivative of the image with respect to the x and y directions. Recall that what we would usually do is not just take the derivative of the image, but we would smooth and take the derivative of the image. But let's kind of skip that detail for now and just say that you're not worried so much about smoothness and that you're only worried about taking the derivative. So if you take the derivative and square it, then that will be high if you're on a boundary. In other words, if the gradient is high, then this thing will be high. But remember, what we want to do is encourage to have the things that we want to encourage have low energy. So that's why we take the minus. So if you're at a very high gradient region, then that will actually minimize that energy because it's negative. It'll be low. But this is, I'd like to emphasize, this is just one possibility for what you can do. You can have this E image encode the fact that you want to have, for example, polka dotted regions on the inside and plaid regions on the outside, for example. Stripes on the inside and snow on the outside. Whatever it is you want. Now the third thing is what's called a user-defined energy. It allows the user, or you, to basically look at the contour you've got and add additional information that is not necessarily about the continuity of the curve or how complicated the curve is. And it's not necessarily sitting there in the pixel values of the image, but it's something additional that you want to add onto it. And this happens all the time in medical imaging data, actually, where in my CT scan of the kidneys, there is a particular structure in there, say the spinal column, that for some reason looks like kidney in terms of its pixel values. I'm just making this up, but let's say it looks like kidney, but because I am a because I'm a radiologist, I know for a fact that it's not kidney. And so my contours might gravitate towards the spine wrongly because I want kidneys. So what I can do is define a landmark, which is basically a point on the spinal column, and say the energy is high if the contour comes close to this landmark. So I'm trying to repel the contour away from it. And again, when I say energy, it's kind of this abstract notion that you are defining as the engineer. Similarly, if there is some feature that is not obvious from the raw pixel intensities, but in some way indicates where the kidney boundary is, then I can put a landmark there and say, I really want my boundary to go through this landmark. So again, I mean, another way to put that is that if my landmark for the spinal column is at position Li, then I can say that there should be a negative here, I think. But basically, the energy should be, this should be a negative actually, so please make a note of that. So basically if, let's see, if the points on the boundary are very close to my landmark, I want high energy. So if this is a distance function, then the distance is going to be low if they're close to each other. And so I want high energy in that case, so I should make that negative. Okay? Or maybe 1 over the distance, that would also do it. And similarly here, if I have a landmark that is on the kidney, and I want the boundary to go through there, then I'll have low energy when the distance between the boundary and the landmark is low. That's what I want. And that, if I sum that over all my landmarks, then basically I will end up with low energy. So again, just to repeat myself, you really want your energy function to encourage high energy for things that you don't want and low energy for things that you do want. And this is just a way of extending that to extra information that you, the user, have at your disposal. So now we arrive at this section called optimization. And ideally what you would want to do is just simply take the derivative of this e, this integral, and set it to 0. Now, the derivative of each one of, if you take that apart, then the derivative of each one of these energy functions individually kind of gives the contour a direction to go in, such that it tries to satisfy that one requirement, either of being not too curvy, that's the internal one, fitting the image data, that's the second one, and moving towards or away from the landmarks, that's the third one. So this is actually the most useful thing you can do to debug your code, in fact. Because what you can do is essentially turn off all but one of these energy terms, turn off e-image and e-user, and simply say, okay, well, if I try to minimize the internal energy, do I end up with something that looks like a sphere? And I should. If I turn off this one and that one, and I just have this one turned on and I minimize it, do I end up with a contour that fits the boundary properly even if it is highly wiggly and ignores the landmarks? Similarly, if I only turn on this one, do I have a contour that goes towards or away from the landmarks as I have specified them? And by adding these energy terms together, you're basically forcing your initial contour, which I guess would be, I'm not sure why the colors turned out like this, but imagine that your initial contour is like this, and you represent the smooth. There's kind of a direction that you can go in to make it the most smooth as possible, to go towards the edges, high gradient areas as much as possible, and to be as continuous or smooth as possible. And really what you are going to do is try to find some kind of middle ground between all three of these requirements. And again, you have this alpha, beta, and gamma, which help you to upregulate or downregulate one of the terms or the other as you see fit. So, and in fact, this is very, very common in practice, where you run your optimizer and you end up with a contour that is just too smooth. It doesn't capture all the little nooks and crannies of your boundary between the kidney and the soft and the abdominal fat. So then what you would do is you would push down alpha and say, okay, yes, being a smooth contour is important, but it's not that important. And so then you hope what happens is that the contour becomes more and more kind of jagged, but not too jagged. So this is how you would optimize these things in practice. Oh, and I have just said this. Another thing is that you, the user, could say, okay, for the most part, most of the contour should not have any of these corners, sharp corners or cusps in them. But there's one location where, yeah, actually there's a corner there. And so for that one, you can set the internal energy term to be exactly 0, so that it doesn't try to discourage that corner from developing. And another way of saying that is that the internal energy will not try to push the contour in this direction, which it usually would try to do to discourage that high curvature region. This is a typical plot that shows you how the contour would want to move if it's in this initial position that you can't really see inside the U, and you have defined these three terms, and you isolate just the image term to tell you about the fact that you want the contour to move towards the horseshoe-shaped boundary. And what you should see is that it does a fairly intuitive thing, which is that wherever the contour starts out, it kind of pushes each individual point towards the boundary that you want. So this is just a graphical depiction of what the gradient of that energy term looks like for any particular position of the control points. Yeah, and this is just a graphical way of showing what I kind of already described, which is that if you have an attracting landmark, it pulls the curve towards it. And the opposite for a repelling landmark, like the one that I said was on the spine that we want to stay away from. So in what's called gradient descent, which is a very common optimization technique, we set the derivative of that energy function to 0, and we move the contour in the gradient direction by a small amount. So remember, if you have a function and you are trying to find the minimum of it, what you would probably want to do is look for spots where the function's derivative goes to 0, because at both its maxima and its minima, the derivative goes 0. And usually in practical settings, we don't have unimodal or uniminimal functions, and so what we do is we simply move around until we find a local minimum of the function by just finding locations where the energy goes to where the derivative goes to 0. So then you simply set the derivative equal to 0, you move in the direction of lower gradient, and then you recalculate it and you move again, and so on. And the trick here is to define how much a small amount is for determining how far you should move with each gradient descent step. And then in greedy optimization, it's not necessarily a different thing from gradient descent, but for each control point, basically what you do is you calculate the energy at where you are, and then at each pixel that surrounds you. And greedily, which is to say you don't think of the big picture, you just think about what I should do locally at this moment in time, you then move the point to the pixel that has the lowest energy around you. And if your current position is lower than all the energy around you, then you stay put. So it's greedy optimization. I already talked about this, but some things that you can do is to add an energy term that you can call the balloon energy, that simply all the time is trying to make the contour expand, expand, expand outwards. Opposite of that would be to add a shrink wrapping energy term that makes the contour get smaller and smaller and smaller. And then if you have a complicated boundary shape, then you can start with many little spheres and then expand all of them and see how they all expand to fill in your region of interest. So one thing that you might be interested to hear is that if you plop down one of these contours onto a completely flat image where there's no gradient at all, then sometimes the optimizer will freak out. And the contour will just kind of arbitrarily jumble, 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 and segmentation fault, core dumped. And another thing to worry about in this multiple contours case is what happens when contours collide with each other. So typically what you want to do is have disjoint regions in the image where each region corresponds to one category of pixels. Well, if these contours overlap with each other, that's no longer well defined. You could, however, add an additional term to the energy that repels contours from each other so that they don't cross each other. So again, this energy thing is very flexible in that it can accommodate different types of behaviors that you want to encourage. Okay, so topological changes are a big gotcha of deformable contour techniques. And part of the reason, or actually the main reason why we want to discourage high curvature regions like this in our internal energy function is that if we don't, the contour can cross over itself. And any contour that crosses over itself is kind of automatically not a very well-defined thing. It's no longer a simple boundary where there's a well-defined group of pixels on the inside and a different, distinct, well-defined group of pixels on the outside. So that's why we have the internal energy function that tries to discourage this case. But the gotcha for that is that is that if you think about it globally, you can have contours where there are no high curvature regions at all. If you go through this whole thing, no part of it is high curvature, and yet it has crossed over itself. So this is just to say that you need to worry about topological changes, aka crossing over itself, at all sorts of different scales, not just locally. Here are some results that you can look at. Just to summarize, 3 things for top-down segmentation with the deformable contours. You have to parameterize the curve. You have to define the energy that squishes your semantic notions into mathematics. And you have to optimize that thing to get curve parameters or contour parameters that have low energy. Last-minute questions from anybody? Okay. Jing's discussion, our office hours are next.